Hello. So this time I'd like to explore this notion of generalized eigenvectors. And to that end, let's propose the following 2 by 2 matrix. So let A be the following matrix. From here, it's not so difficult to see that the determinant of A minus T times identity T being a symbol is nothing else but 2 minus T squared. So the only eigenvalue of A is lambda equal to 2. And we know that its algebraic multiplicity is 2. We can extract that from the complete factorization of the characteristic polynomial. And well, to compute the geometric multiplicity, we will have to find the dimension of the associated eigenspace. And for that we need a description. So one thing that we can do is to find a basis for such a thing. So to that extent, let's find a basis for E lambda 2, so the eigenspace, which is nothing else but the null space of A minus 2 times identity, which is the null space of the matrix 0, 1, 0, 0. Well, let's not forget what this means. This is the collection of all those vectors x1 and x2 in R2, such that when we multiply the matrix 0, 1, 0, 0 times x1, x2, we get the 0 column vector. Careful analysis of this set tells us that an element, a vector, is here if and only if we have that we can write x1, x2 simply as, well, look, this product imposes only one condition, that of x2 being 0, and that leaves x1 in whatever thing that we want. So we can expand this in this fashion, and that means that from here we can deduce that the eigenspace associated with 2 is nothing else but the span of the set containing the vector 0, 1, 0. In other words, the geometric multiplicity of lambda equal to 2 is 1. So in this case, we say that the matrix is defective. Right? But defective in what sense? Well, defective in the sense that we don't have enough eigenvectors, meaning linearly independent eigenvectors, to come up with a basis of R2. So we have to extend this notion, and one of the ways to do it is to try to solve this problem. So we can extend this collection, this collection 1, 0, to be a basis of R2. But with the following condition, we'll do it in such a way that we generalize this vector. In what sense? Well, in the following sense. Let's find a vector W in R2 such that A minus 2 times the identity times W is equal to V. You see, uh, in other words, this would be something along these lines. Being able to produce, right, uh, a vector for which this is 0. Right? Of course, this is going in this direction. This may need further clarification. But well, we'll leave it to this extent. Okay, so let's solve this. That's not such a complication. To that, we have the following conditions: 1, 0, 1, 0, 0 times the vector w, which I'm going to describe as w1 times the w2, being equal to the vector 1, 0, which is the one that we use to generate the span of this collection and generating the eigenspace associated with lambda equal to 2. For this, we have the following set of conditions. Whenever we see this, we may expand it in the following way, performing the usual multiplication. This indicates that W2 and 0 is equal to 1, 0. That happens exactly when W2 is 1. So we have that W1, W2 is equal to whatever we wish in W1, but with a 1 here. So in particular, when W1 is 0. And look, in this case, we have that the collection composed of 1, 0, which is the vector that generates linearly the eigenspace associated with lambda equal to 2, adjoint with the vector 0, 1, well, forms a linearly independent set and thus generates all of R2. In one way, we would like to say that this resolves the defectiveness of the matrix A. Of course, to understand this in full detail, we'll probably have to introduce the notion of invariant subspaces. But well, for that, we'll leave it for a subsequent video. Let me know if you would like to further into those topics, and let me know in your comments if you like this development. Take care, subscribe, see you around.